you see me collapse to the floor, you can summon appropriate assistance. I do have what I believe is a cold, and I'm keeping my distance here. For this lecture, we're really discussing the final little sort of component of discussing issues that are specific to system dynamics modeling only. We're going to be talking about a number of processes that apply to system dynamics model, but they also apply to agent-based modeling and to some degree to discrete event modeling. Things later like sensitivity analyses, calibration, model debugging, those sort of things. Here we're going to be talking about some issues related to building up these models. It's possible, depending on student interest and projects go, it's possible I'll spend 1 or 2 sessions talking about some things very specifically with more advanced things in Vensim. So if there's an interest in that, I might do that. But this is really sort of the last lecture on building the pieces, the building blocks out of which we build system dynamics models. It continues on some thoughts we had last time for equilibrium behavior and issues with higher order delays. We had may have introduced this principle last time. Certainly in the video you might have seen it. Structure is shaping behavior. So when we think about a system dynamics model, we think of a system structure as defined by stocks, flows, and connections between them, interconnections between them. And actually, when we say flows here, well, you tell me, stocks and flows. Which of those do we have to explicitly specify the equation for? Flows. Yeah. Flows depend on stocks. The flow over the next period of time depends on the stock values for the current period of time. Why don't stocks have a formula? Why don't we have to give a formula for a stock? It's determined by the flows. It depends on the flows. Okay. Into or out of that stock. So if the inflow is greater than the outflow, the stock rises, and vice versa. It reduces over time. It lowers over time. So we talk about system structure being defined by these, and there's a principle that that structure drives behavior. The behaviors you get out of a model depend on the structure of that model. Now, at a certain level, this may seem obvious. After all, that's what the model is. So, of course, it determines behavior. But actually, at deeper levels, it's a very important point. A given model can't necessarily reproduce all behavior. A given model structure will only be capable of producing certain types of behaviors. Okay? If you see an oscillation, that can only come about from certain types of model structures. If you see growth and plateau, you see an overshoot and collapse. These are all things associated with certain types of structures. And because of the phenomenon of nonlinearity, we could say the behavior of the model as a whole is greater than the sum of the behavior of its parts. You can't just take it apart into each stock or each flow in isolation and expect to analyze the behavior of the model as a whole completely. Instead, there's sort of this intermixing. We talked about feedback loops that compete or that interact. One dominates another, for example, over time. The behavior coming out of a stock and flow model transcends the behavior coming out of any one piece of any one stock. And so we get certain behaviors out, and they speak to us about sort of the underlying structure of the model. And try as we might with certain model structures, we're not going to be able sometimes to match certain types of behavior. So if we have certain behavior modes, we might try hard as we can to reproduce those behavior modes by tweaking parameters. We're just not going to be able to do it. It's something about the structure of the system. So oscillations are a good example. You're not going to be able to get an oscillation with a single stock without actually forcing it somehow by putting in a sine wave explicitly in the formula of how that stock, the flows depend on the stock or what have you. So if you have normal sorts of relations, they're going to give rise to certain characteristic types of behavior. And later we'll see when we calibrate a model, how successfully it calibrates will be a function very much of its structure. And sometimes we can't calibrate it effectively against certain data. We can't match its behavior against empirical data, against observed data, well, because the structure is off base. And so it points us to the structure and says either the data is off base, lets us look into that, or the structure is off base. Okay? So those are some sort of comments on